Okay, so we are now recording. So I will say a welcome again to everyone. This is a EXA webinar brought to us this time by SOCIO-BEE, and we will be talking about air quality. And we have today with us 4 experts on this field who will be presenting different parts of this big topic. We have Nuria from NILO, the Norwegian Institute for Air Research, which is a research institute whose core mission is to contribute with knowledge for a clean atmosphere. We have Eduardo from HOPU, which is a company developing human-oriented products that enable us to tackle big human challenges such as air quality. We have Sergi and Francisco from BETAIR, which is a company that empowers cities and communities to effectively mitigate pollution by providing actionable and reliable data. And these will be our experts for today. But before, we will start with a small introduction to our project. So we're all here from SOCIO-BEE, which is a project that is committed also to creating opportunities for tackling clean air issues. And so here with us is Vangelis, which is the coordinator of our project from CERT, which is, as I understand it, is a group of institutes that are all conducting research with the aim of transforming scientific knowledge in big areas such as air quality into innovative and technological applications. So with that, I pass on over to you, Vangelis.
Thank you, Carolina. Hello, everybody. I'm very glad to join with you in this very interesting event. I tried to start my camera several times and it failed. And this is not the problem of my camera because some minutes ago we have a normal operation of my camera in a call with global with GoToMeeting. I don't know, so apologies for this. I can share now my screen to provide a very brief introduction to the project. Can you see my screen?
Yes.
Okay. So the SOCIO-BEE project, it is a European project, of course, funded by the European Union in the framework of Horizon 2020. The project is focused on investigating the use of wearables and drones in a smart way that will lead to engagement of citizens, produce initiatives from the citizen side, and all this endeavor will hopefully lead to initiatives for better quality of environmental conditions in European cities. This is the overall approach. I'm Vangelis Kopsachilis, and I'm reproducing CERT, which is the lead partner of this project. As I can just say, the project, the wider frame where SOCIO-BEE will create is in the Green Deal call, which is focused on how to enable citizens to engage and act for environmental improvement of their cities. One key aspect of this topic is that the concept of citizen science should be focal. We have to use citizen science approach to achieve this goal for the environment in the European cities. Now, some numbers are always interesting to explain the background. The cities in Europe concentrating a huge percentage of the total population. It's about 75%, which represents 340,000 million people. The air pollution, it is probably the main environmental challenge in the urban environment. Of course, a problem that has been created since last decades and getting worse with time. An important role in this challenge plays the consumption of energy for mobility and also for production in industries. And we had also a very interesting observation due to the pandemic of COVID-19, where we have lockdown in many cities, and due to the reduced mobility of the citizens, the pollution of air has a decrease in the range of 17%. That indicates that even for a very bad reason, which is the COVID, we had the opportunity to observe that if we change the behavior, we may have direct impact on the environment. So these numbers are very indicative to show the potential that initiatives engaging citizens may have on the environment. And as is already mentioned, in order to achieve such endeavors, we need technology and a change on the behavior of the public. Of course, in order to be such endeavor realistic, it will be based on the collaboration between different stakeholders like citizens, businesses, decision makers, and so on. So if we try to summarize the vision of our project, is then first to use the supporting technologies. You can see here some indicative artwork with drones, communication information technologies, smartphones, wearables, so on. In parallel, we shall need to deploy engagement strategies in a smart way, in a well-informed way, to create the hives, the SOCIO-BEE hives. I will say a few words about these hives in a minute. So these
Vangelis, you have 1 more minute, okay?
Okay, thank you, Carolina. I was okay. So the whole we will use these 2 pillars to create monitoring campaigns that hopefully this will lead to behavioral change. Here is an illustration of our solution, which is focused more on technological aspects. We have here the sources of pollution. We get some measurements using sensors of pollutants. The sensors could be wearable or drones. Then we concentrate the data into a platform. We apply artificial intelligence and recognition techniques and many other tools to produce analytics and insights. And then we have the vision to transform them into policy making, campaign making, motivation of citizens, and things like that. It is interesting to say a word about the beehive metaphor that will justify why we use green and yellow and black colors in the bees. We imagine that the SOCIO-BEE will create hives of citizens that will be coordinated by informed persons that may lead the group, the hive, and we have named them queen bees. They will engage and motivate worker bees to collect the data. We have also some drone bees that will make observations. So all this effort will produce some tangible result, which is the honey in our paradigm. The honey, of course, always is stealed by the honeybees. So we will give the honey to the honeybees, which are this role is the decision makers, the policy makers, the entities that could take action to improve the environment. The project foresees 3 pilot sites in Spain, Zaragoza, in Italy, Ancona, and in Greece, Amarouson, a nice suburb of Athens. They have different aspects of air quality problems, but they all have air quality problems. So our pilots have a little bit of overlapping, but they are not identical. There are 3 pilots that are complementary. SOCIO-BEE will be implemented by a magnificent consortium of 18 partners from 7 countries. We can see here their logos. Unfortunately, I don't have time to present the uniqueness of each one. I'm sorry for that. And I will close my short introduction by this information. Many more details and information are available at our website. You can see here the URL. And you may follow us on Twitter and LinkedIn for further updating with living information and so on. Thank you for your attention. Again, apologies for not being able to enable my camera. Apologies for that. And I would like to wish you all to have a very successful and a very productive webinar today. Thank you.
Thank you so much, Vangelis. So now I will pass on the word to Eduardo, who will tell us a little bit about history behind a historical review of pollution and the different types of pollution. Eduardo, I'll tell you when you have 2 minutes to go, okay?
Okay, perfect. Thanks really much, Carolina. And I would like to start thanking to the SOCIO-BEE consortium to give me this opportunity to participate in this webinar. And I have to say that it's I'm so glad to be here. So let me share my screen. No, sorry, wrong. Sorry, it's so can you see the presentation?
Yes.
Okay, perfect. Now can you see the presentation in the big mode?
Yes, we can.
Perfect. So let me present a bit. I'm Eduardo Fernandez I'm data scientist from HOPU, and I'm also performing my PhD in air quality modeling and air quality forecasting. So the first part of this air quality crash course is focused on a brief historical review of air pollutions and types of pollutions. And I would like to start presenting you an event that occurred some years ago in Donora in 1948. In Donora is a city, is an American city in Pennsylvania, and the problem that they had is in these dates they observed a intense smog covering all the city. This smog was due to the pollution of the industry that are present in this city, and this event was really shocking for this city because it affects nearly the half of the town's residents. And they experience it severe respiratory or cardiovascular problems over 5 days, and nearly 40 people died due to this fall. So this event had strong consequences. So despite pollution was no stranger for Donora pollutants, because as I said before, it was an important industrial city. The problem was that the meteorological conditions due to the meteorological conditions, the air and the pollutant wasn't able to left and to escape. So these strange situations reflected a warning trend in the and this warning message was that air pollution had become a harsh consequence of industrial growth across the world. So many years later, well, this event has a strong impact in American citizens, and many years later, it was approved the first law related to air quality, that was the Clean Air Act. This law and other legislation that starts to appear later are based in the interaction of three different fields, knowledge fields. The first one is natural science related to climate change, air quality measurements, and these natural science are the basis of political science that is based on political decisions to reduce this data that we collect with this science, and also taking into account a philosophy and especially an ethics in the process of decision making. So after this brief historical introductions, I would like to pass to the classification of air pollutions, because then I will use some of these concepts. We can classify air pollutions in function of the source. We can talk about natural air pollutions and anthropogenic light pollution if the cause are human activities. We can also talk about the type of emissions. We talk about primary emission if the pollutant is emitted directly, and secondary emissions if the pollutant is formed by chemical reactions from other pollutants. And also another important type of classifications is the type of gas. We say that a gas is a pollutant if this gas has a nocive effect in the people health, in the population health, and a greenhouse gas is a gas that contributes to the global warming. This is important because there are different gases that are pollutants, for example, NO2, O3, CO, and other gases that are greenhouse gases. For example, the most common is CO2. So then I will do a brief review of the evolution of different pollutants, of different emissions among the last years. I will do this review starting for greenhouse gases. Remember, gases that are related to global warming, and then to air quality pollutants. So let's start for the most famous gas, that is CO2. And in this graph, we can see the evolution of this pollutant among the last years, starting on the industrial revolutions, and we can see an important increment starting around 1915. That's 1950. It's more or less the so-called the second industrial revolutions, and we say that this increase is especially related to human activities related with fossil fuels and this kind of activities.
You have 2 minutes now, Eduardo.
Okay, we say a similar trend for other greenhouse gases, and this is about emissions. And if we move to pollutant gases, we can see an important effect, that it's the emissions of these pollutants are reduced over the over the last 20 years due to the European legislations. As we can see, we have here NO2, SOCO2, PM, CO, black carbon. So it's true that we are reducing these pollutants, but not the greenhouse gases emissions. The same occurs with metals. So if we analyze now the air quality evolutions, we can see that for several pollutants, this air quality evolution is reducing also during these last years because the reductions of the emissions of pollutants. This is an example for PM10 from different areas, rural, urban, traffic, industrial. And the same occurs for other pollutants like PM2.5, NO2, SO2, and SO2. All this shows the same trends among these last years. But are these, the question is, are these reductions enough? Then we need to take a look into the other side, because it is true that in the recent years, the population is increasing, especially the population in city. So if we could take a look of personal exposure, that is how many pollutant is affected each person, a single person, we can see that the trends are stable in the last years. And I would like to finish that nowadays, the personal exposure, according to the EU standards, it's okay due to the European legislations, but the recommendations about the World Health Organizations, we are exposed, so a high concentration that the World Health Organization recommends, and that is the strong challenge that we have to affront in the next years. And thanks really much. I hope finally to be in time. And this is a little bibliography if someone wants to know about the air quality pollution in the last years. This is the two most important reports in Europe and over the world.
Thank you, Eduardo.
Thanks very much.
Thank you. If you have questions, there'll be time in a bit, but please feel free to put them in the chat. And now we will go to Nuria, who will tell us a little bit more about what is air pollution and why is it so important to breathe clean air. Nuria. And Eduardo, if you could stop sharing.
Yes.
It's working. Okay.
Okay. Perfect.
You are muted, Nuria.
Sorry, thank you very much. So I was just saying thank you to all of you for attending this crash course. I will be talking about the importance of breathing clean air. I'm a senior scientist at NILU, and I've been working in the topic of air pollution for 20 years. At the beginning, I was working also with monitoring and modeling and a little bit of the classic science, if one can say. But now I moved to NILU, and there I started to coordinate a group of sensor technology and society. And here I would like to say how important is both things, the monitoring and the society, and for whom are we monitoring and whom we want to involve in the monitoring, and the importance of citizen science in all this world. And if we want to solve the challenges that we are experiencing in this era. I am also the chair of the Extra Air Quality Working Group, and I invite you, all of you, to join us. And with that, first question, is the air we breathe clean? According to the World Health Organization, they told us some statistics that we can see in these infographics. When say 9 out of 10 children worldwide do not breathe safe air. And I think that alone speaks for itself. Also, they say like air pollution was responsible for 7 million premature deaths in 2016. So those figures should be able to alone move politicians and authorities and citizens to do something, right? However, we might think, okay, that happens in other countries, but what about Europe? Do we breathe clean air in Europe? And here are some figures from a latest report from this year in the European Environmental Agency, when it says that 96% of Europe's urban population was exposed to fine particulate matter above the health-based guidelines. And that means we are exposed to pollution, and this pollution is causing us problems with health. This is a little bit like the same figure that Eduardo was showing, where we have the EU standards and the World Health Organization's guidelines. I would like to say that there is no conflict in between those two, even if the numbers are very different. The EU standards were started in 2008 when we have this directive, the first directive we had in Europe for protecting human health, right? Like, and there were much fewer studies than we have nowadays on air pollution. Still, like, we see how at the beginning those figures were very different and still like high exposure of population, but now we managed to reduce air pollution, as Eduardo was showing. But more studies are telling us that there is no safe limit, that even like when we are exposed to low levels of what we were thinking are low levels of air pollution, we still experience health problems. So then it's these new guidelines that were released last year from the World Health Organization, when we have these incredible figures, still like 96% of the population is exposed to fine particulate matter, and like 95%.
Checking her time. Do you know when she started?
No.
In light of that, the European Commission has launched the Zero Pollution Action Plan, and also the EU directive is nowadays being reviewed in order to adopt more tight standards that are closer to the World Health Organization. So we hopefully in the next years we will also see changes. And COVID has shown us many things, but some of the positive things that have shown us that it is possible. It's possible to lower air pollution. And we saw here, one of the images where some of the traffic lines were devoted to traffic, to bike lanes. We need to see more of those in our cities in order to lower air pollution. What is air pollution and where it comes from? So air pollution is actually like the introduction, is defined as the introduction of harmful substances to the air. They can be gases or tiny particles. And here you can see this is the image of a hair. And here is like the PM, what we call particle, like coarse particles, PM10. You can see they are like really, really tiny. And if you go to fine particles, the ones that we were saying we are most exposed and more harmful to our health, you can see like how tiny they are. So to our eyes, air pollution is invisible. And where does it come from? It has different sources, like traffic, also like heating in our houses, shipping and the port activities and industry are some of the main sources. And they contribute to both pollutants that affect our health and also greenhouse gases that affect the climate change. The difficult thing always with pollution is this, that we have new technologies, alternative fuels, and they release new compounds. So the research on air pollution is a never-ending story. Also, like just a brief, it's very different when we talk about emissions than when we talk about pollution. Emissions is what is emitted directly from the source, and then that emissions go and travel with the air, and it might be clean with the rain, and also they might even react among themselves and creating new pollutants. So when we study pollution, we talk about all those transformations, like chemical transformation and dispersions on the air. So something that is emitted, maybe in an agriculture field, can be traveling to our cities and impact on our health. And how are we measuring this? We have sensors, wearable drones, and air quality stations. There are pros and cons in everything. Like we have been monitoring air quality for a long time right now. This is like if you see on the left, you have the traditional air quality monitoring stations. They are complex, they are huge, they are indeed very accurate. So we still need them. And here we have this new development, the low-cost sensor platforms as the ones that we will be using in SOCIO-BEE. They're small and portable, they're easy to operate, and we can create dense networks and monitoring in places where we are not monitoring right now. But still, like, we have to deal with the high uncertainty of the sensors. This is how an air quality station looks. You can see here lots of cables, lots of monitoring and equipment, very expensive. And this is how it looks outside. No, this is one in Oslo, like a little metal box. And those are from those type of stations. This is the coverage we have in Europe. And one might think, wow, it's quite a good one, right? Like we are lucky in Europe. We have many stations following how is the air pollution and how it's affecting our health. And they are very accurate and give us this overall picture, but they lack detail. So if we zoom in into two of the cities that I know well, Oslo in Norway and Kristiansand, we see Oslo has a population over 1 million. It's still a small city, but a bit large ones for a Nordic country. We have quite a few stations, but there's still many gaps in between, right? But if we go to smaller cities like Kristiansand with almost about 100,000, we see only 2 stations here, right? Like really a lot of people do not have individualized information on air quality. So that is where sensors and citizen science can really make a difference. And this is the same cities, Oslo and Kristiansand. And here, all these dots, those are sensors installed at citizens' houses. And also, like, we have bikes that are monitoring. So you can see, like, what is the big difference when we engage with citizens providing air quality. So thank you very much.
Thank you, Nuria. Right on time. We have a few minutes for questions now. So if anyone wants to raise their hand and ask a question. Maybe whilst we wait, I would ask a quick question. Nuria, you were talking now about this, the power of citizen science in helping us get the data we need. Do you also think, or maybe you can say a few words, do you also think that this can also help? I guess there's a lot of inequalities with countries who have more resources being able to produce more sensors and measure more. So do you think citizen science can also help us bridge that gap, so that we have a fair representation in the data we collect also?
Yes, I believe so, right? Like that we can really, like, it can be something that is especially important in developing countries, and also maybe in countries where there is not such maybe a corrupted government or government that do not really take or take care of the air quality, right? And that's where the citizens can contribute. But here I wouldn't like to talk about the global north and the global south. This happens in both, you know, like where we have, and it's still in countries like in Scandinavia, we still have many inequalities, and when we are even in citizen science, no, when we are distributing sensors. So we see as in citizen science that mostly are like men or like maybe overeducated people that are participating because they do have maybe more time, right? Like so, hopefully in this project we will reach to other population that is usually not so engaged and bridge the gap.
I guess we all have the same vision as you. Anyone has a question? Maybe I tried to write down the question for you, Eduardo, but I guess I wasn't very clear. You said something about the classification of gases and how one is considered, I don't know if you used the word toxic or bad in general, if it's harmful for human health. And I was wondering if there are gases that maybe are harmful only for certain animals, but not for humans. Are they then not considered harmful?
Yes, that is an interesting question because always we have an anthropogenic vision of these things. But as I understand, in the European legislations, these are defined as air quality pollutants that are included in the air quality index calculations and air quality monitoring are gases that has a nocive effect in humans. Of course, there are a lot of gases that are a very harmful effects for maybe animals, plants, or in general the environment. And also there are more gases that ones that are defined in the European legislations that have nocive effects in humans, but this effect is lower than this one that are defined. As always happen in classifications, are always a bit strict and the limits are difficult to, and it's difficult to establish the limits between groups.
Thank you. So it is very important what we're all working on then.
Yes.
Okay, so if there are no questions, you can still ask them later on. It's not a problem. I would pass on to Sergi, who will tell us a little bit about technologies around the things we've been discussing. And again, I'll also let you know when you have 2 minutes, Sergi.
Thank you, Carolina, very much. It is a pleasure to be presenting here in front of this involved audience. I will be talking about technology solutions for monitoring the different dangers or the different problems of air quality in the atmosphere. Basically, let me see, how can I, why is this not? See the response, yes. Basically, we'll be talking about the toxic pollutants in organic and organic, particulate matter and greenhouse gases, also how we can measure them and how we are actually measuring them. I will not be talking, and I want to link this to the last question that was asked here in the webinar, which about the influence of in animals. There is another technology which is very underdeveloped, which is bioindicators, a very interesting technology. I will not be talking about it, but it is a subject of a lot of interest. But it's not currently something that has the accuracy or the development that allows us to do accurate measurements. So first of all, toxic pollutants, they have an effect on health from when they are in high proportion. One of the main ones is the nitrogen oxides, mainly nitrogen dioxide, but also the other oxides. We need to measure these toxic pollutant down to the ppb level, because this is where the health effects start to appear. This is a very low level. It's a parts per billion. It's a very, very tiny concentration, but we are already sensitive to that. There is the possibility of measuring them with electrochemical sensors, which react with the gas with a fine-tuned designed reaction, and they produce an electrical signal. This is a common approach for measuring this gas in compact sensor systems. But it also has very strong effects in interaction with ultraviolet light and infrared light, and in particular, it's photochemically active in the ultraviolet region. And this is used as a reference method to detect the nitrogen dioxide and the nitrogen oxide by different technologies. One of them is the cavity attenuated phase shift, but there are other more generic photochemical reference systems. This photochemical activity is actually the origin of what is called the photochemical smog that we can see here in the photograph in the right. I think you cannot see my pointer. Can you see my pointer? Laser pointer, yes. Okay,
Yes, we can.
Okay, now you have it. I like this. So this is a photochemical smog example. This particular color is produced when first the ultraviolet light splits the nitrogen dioxide into nitrogen oxide, nitric oxide, sorry. And then when it recombines with ozone, there is a crosstalk with ozone, and then it emits light in the infrared. It shifts to the red. So this is why this color is like this. And here we see an image of a reference analyzer for photochemical based on photochemistry that we can find from thermoscientific in reference stations, the reference stations that Nuria mentioned and we will mention later on. An example of the concentrations that we can see in cities for nitrogen dioxide would be this graph here. We can see here the concentration in parts per billion, so a very, very fine, very accurate concentration, and what happens in rural background, some kilometers away from the city, and what happens in the city itself. We can see here peaks around the lunchtime and when people finish the working hours, and also in the morning. Obviously, the people get to work, and we can see several peaks, mostly related to the combustion of the cars. This is a typical electrochemical sensor, and here a 2 euro coin for comparison of the size is a compact sensor that can be found, as I said, in compact systems. And this is an example of a reference system for reference stations. And as we can see, this is much larger, this system. And then, of course, you need the fluidics to bring the sample here into the system. And so it's quite more complex. There is also ozone, one of the main toxic gases that are being measured currently. Ozone, we know ozone because it's very vital, and in the stratosphere, we can see here the ozone layer. It shields us from ultraviolet radiation. This is already giving us a clue that the ozone is active in the ultraviolet, meaning that this can be used to measure. It has a strong absorption bands, very strong absorption bands in the ultraviolet radiation. But when we find ozone here, down here in the troposphere, and to be more exact, in the planetary boundary layer, which is the part of the troposphere that is directly influenced by surface activity, when we find it here, it's toxic. It's toxic, and we also need to measure it at very high accuracy in the ppb level, the parts per billion level. As I said, there's also the possibility of measuring ozone with electrochemical sensors, similar to the nitrogen dioxide. But for reference technologies, it's typically the ultraviolet absorption bands that are used, the very marked ultraviolet absorption bands, and the infrared. So this is sort of spectrometric techniques that maybe I will elaborate a little later about what this spectrometry is. It also has this photochemical activity with nitrogen dioxide, as I mentioned before, and this is also something that can be used to measure. Let me see. Why is this not going forward? Okay, now. Another very, very relevant inorganic pollutant is sulfur dioxide and the sulfur oxides. It is a colorless gas with a choking or suffocating odor. So the odor of sulfur is pretty. It normally you smell it before it's really toxic. But still, it can be very relevant, as we see here. This is actually a forecast based on many reference measurements, mostly from the satellites of the European Union that I will talk about later. And this is the plume related to the eruption of the La Palma volcano in last winter. So this is a forecast of what sort of pollution could be expected in the different countries, no? And taking into account the different weather parameters to simulate, to forecast what could be happening, important for different aspects, aviation and so on, but also toxicity. Sulfur oxides can be measured through infrared or ultraviolet absorption, but most reference methods use a special fluorescence, a special also photochemical effect fluorescence that SO2 has with ultraviolet light. When excited with ultraviolet light, it shifts. There is an excitation. The excitation cycle of the molecule that irradiates radiation in a measurable band. Then when we move on to organic pollutants, they are much more varied. There are many families and many different organic pollutants that have an effect. Polycyclic aromatic hydrocarbons is a very wide family, which are byproducts of organic matter combustion processes. Usually, benzene is a typical also pollutant present in a lot of industrial processes and also vehicle exhausts. And I highlighted here the different structures. So organic molecules are typically very simple in structure. And here we can see here a polycyclic aromatic hydrocarbon. This is a schematic representation, a more elaborate standard representation here. And here, very nicely, this is actually an atomic force microscope image. This is actually an image of the molecule itself. We can go down to this resolution. It's also funny because you can see the hive here of that is our logo here. Not related to this, obviously, but I liked very much the image, so I wanted to put it in here. The typical reference measurements for this sort of measurement, for this sort of pollutants, is gas chromatography with sequential sampling. What does sequential sampling means? I will go in the next slide about this. Also, real-time monitoring is achievable with some solid-state sensors, electrochemical sensors, but here accuracy is difficult to achieve because of the many different families and different structures of the organic pollutants. It's difficult to get accuracy without GCMS analysis. The GCMS analysis is done by basically there's a sequential sampling in this sort of instruments. For instance, they trap the air during one day in an absorbent phase, in an absorbent, so to say, device that absorbs the organic pollutants for one day, and then they switch to another channel for a second day, a third day, and then probably every week the expert will come, collect the samples, and do an analysis in laboratory equipment, in a typical analytical chemistry, in a reference analytical chemistry laboratory. So this is the way. This sort of equipment is placed, as Nuria mentioned, in a reference station. In those complex reference stations, we typically find this sort of sampling devices to analyze organic pollutants. Now, another very important pollutant is particulate matter, because it has very strong and well-documented effects on respiratory system of the people. The particulate matter is also a conventional or a typical measurement that is performed in reference stations. We see here 2 reference stations in Germany. And I highlighted here the inlets, the typical inlet shape that we can identify that is dedicated to particulate matter. The typical reference instruments that are used for particulate matter measuring incorporate these large inlets, and then there's the possibility of doing real-time analysis with a mass transducer, which is something that is responding to the density around and changes the frequency of vibration, and then we have an immediate response of the changes in the ambient of where the reference station is located. And this is used for important events, special contamination events, and to issue warnings and so on. Sometimes also here, instead of a mass transducer, an optical transducer can be used. I will explain more about the optical principle later. There are other sort of reference instruments that that filter that can use a special fluidics to filter part of the particles that come in. So you either can measure all the particulate matter. You can measure ranges of the particulate matter, the fine particulate matter, the coarse particulate matter. This is related to the size. If they are less than 10 microns, less than 2.5 microns, they receive different. They are different, have different origins, have different effects also, and also they are measured differently. Here we see in the right, this equipment, for instance, can differentiate two different sizes. It splits the flow and uses different filters. And at the same time, these two systems here, one for one type of particles, another one for two types of particles, have a different measurement principle. I told you before, of real-time mass and eventually optical detection. Here, the particulates are captured in an accumulator, in a trap. This trap is similar to the organic pollutants trap. This one is a trap for particulate matter. And this trap is also collected regularly, weekly or so. And then it's
2 minutes, Sergi.
Thank you, Carolina. And then is weighed in a scale, in a laboratory scale, and then the flow that flows through this trap is very carefully controlled, so now you know exactly what has been the concentration of particles during one day and every day of the calendar. So it's a daily sampling normally as a reference. I mentioned the optical principle. This is the principle used in practically all the compact sensors, because there are compact sensors to measure particulate matter that are widely used, and they are not so accurate as the reference systems, especially for the larger particles. But as I say, they're very widely used and they have very good results in compact devices. They use a laser or a light source to illuminate a flow of particles with very well-known flow rate and localized. And then a photodiode is used to measure the scattering, the reflection, the different effects that the particles have on the light. After this beam interacts with the particles, then it is absorbed by what is called a beam dump that avoids any further reflections. And so this is a very common principle for real-time measurement of particulate matter. And there are many different manufacturers and systems. We see here how compact they are. We can see here 2 euro coin for reference. And they have different characteristics, but all of them have a pretty good performance in the fine particulate matter range. Black carbon is a particular type of particulate matter that is especially studied because it gives information about the origins of where it comes from. It's been related strongly to combustion process and to the combustion process of organic matter. Since this particulate matter is also have health effects, but the nice thing about measuring the black carbon is that it can give you very important information of the generation of this sort of particulate matter. It is using what is called an aethalometer, which is right, and as of today, it is a common instrumentation found in reference stations. It estimates, though this is disputed, but it estimates the percentage of those range of particles that are originated on biomass burning. This is debated.
Sergi, you're out of time.
Okay.
I think you could wrap up. Thanks.
Yes. Let's go a little bit, only briefly, over the remote sensing methods. I've mentioned about the methods placed in reference stations and compact sensors, but one of the most important sources for information on pollution is methods that use satellite and remote sensing. Basically, there's differential optical absorption spectroscopy in lasers. The spectroscopy, basically what it does is it measures in the different radiation wavelengths the absorption of the atmosphere, and then depending on the peaks that you absorb, you can identify different components of the atmosphere. There's other techniques like the light detection and ranging and differential absorption lidar used in satellites. And the state of the art is, for instance, for the European Space Agency satellite, the Sentinel, uses what is called the tropomi with 4 different spectrometers on board, very high accuracy, and this is providing open data regularly and for the different stakeholders interested in air quality at high accuracy. There is also reference methods for measuring the greenhouse gases. Mostly, I would say that they are very similar to the remote sensing method that I mentioned. So basically satellites. And this is the reason of this is that you are interested in greenhouse gases not at the human level, at the planetary boundary layer level, but in the whole atmosphere, that they contribute in the whole vertical of the atmosphere. So this is why it is more convenient to measure with remote sensors that can integrate the influence in all the atmosphere or identify the influence in all the atmosphere. So since I am out of time, I will close the presentation here. I am open to questions. I have a lot of side material if anyone is interested in one of the particular issues. But that's it for me. Thank you for your attention.
Thank you so much, Sergi. We will hear from Eduardo again, and then we will have again some time for questions. And I see there's already an interesting one in the chat. But before that, Eduardo will tell us a little bit now about, will give us an idea of a spatial and time distribution of the things we've been talking about. Sergi, if you could stop sharing your screen so Eduardo could share.
Thanks very much, Carolina. I will share my screen again. So can you see my screen, my presentation?
Yes.
Okay. Okay. Hello, everyone. Now I'm going to talk a bit about spatial and time distribution of air quality pollution in this talk of the air quality crash course. And I want to start remarking something that Nuria has explained before. And this is the fact that emissions and pollutions are 2 different concepts. As Nuria explained, emissions are the gases that are directly emitted to the atmosphere, and pollution are the concentrations that we measure at a certain moment in the atmosphere. So it exists a process that changes the value emitted to the value observed, and this one is that we call dispersion. So air quality dispersion is the explanation of how emissions are transformed in air quality concentrations in the atmosphere. This is really important because we need to know the air quality concentrations in order to evaluate the impacts that these pollutants could have in the human health and to take decisions in order to reduce emissions and to reduce these impacts. So a formal definition of air pollution dispersion, it is the description of how pollutants diffuse in the space and in the time into the atmosphere as a function of emissions. In other words, it's the explanation of why we observe these air quality concentrations in these locations and in this time in function of the emissions that we have quantified in a period of time. So I especially I would like to remark in this talk what are the most important factors that affect this air quality dispersion. The first one, as I have mentioned before, is the emissions, where the emissions are greater. The air quality concentration is greater, so more pollutants are dispersed. So it is the principal factor, but also there are other factors such as the meteorology conditions. The most important are wind speed, but also there are other important factors. For example, the cloudy situation of the atmosphere, because this affects to the soil. This could affect to some chemical process, also solar radiation, and so on. Also, the atmosphere turbulence, it's really important in the dispersion and the movement of the pollutants, and the topology of the spatial domain, because this topology could affect, or these natural barriers could affect of which paths can follow the pollutants in these dispersions. And another factor that it's really important is the kind of source, in the sense that we can have a static source that are always in the same point of the space, and mobile source. For example, an example of a mobile source is a car, and a static source could be an industry. So all these factors affect in the dispersion in two ways. We have on the temporal distributions that explain how pollutants evolves along the time, and also the spatial distribution. Regarding the temporal distribution, we can see here in this graph that the air quality observed in different months of the year, it's really different. For example, the most important is ozone, O3, because we have that the concentration of O3, it's greater in the summer months. This is the reason is that O3 is formed from NO2, because NO2 dissociates due to solar radiations, and these months that are the months where there are more solar radiations is the most correlated with O3. And about spatial air quality dispersions, I want to focus in some environments that we can find in the cities, because cities are the most important environments, because it's the place where the most part of the population live. So it's important to remark that the buildings and the height of the buildings could affect a lot in the dispersion of the pollutants, because we can observe here a phenomenon that the pollutants could remain at the bottom of the streets if the buildings are so high. So these high quality dispersion studies are so important in order to do a smart urban planning. And another important phenomenon are thermal inversion, that in normal conditions, the warm air is on the bottom and the cold air is on the top, and this allows a diffusion of the pollutants to the layers on the top of the atmosphere. But in some conditions, especially in so polluted cities, there are these situations change. There are inversions, and we have a warm layer that is in the middle, let's say, and here in the bottom we have a cold layer. So the pollutants could not escape due to the warm layer. It remains into the city, affecting for a more period of time the citizens. So it's so important to understand this air quality dispersions, this pollutant dispersion, and for this, the tool that we have are mathematical models. Mathematical models are representations that explain how this dispersion could occur and how this dispersion will occur in the future. So this allows us to do some predictions. These models work with emission fluxes per chemical species. We need to know the emissions, and we also need to know the meteorology. So if we know these two inputs, we can compute the chemistry and transport, and we can obtain this heat map with the distribution of air quality.
You have 1 more minute. Sorry to interrupt.
Perfect. So just to finish, I want to show you some of the most important air quality models. We have two kinds of air quality models: Eulerian models and Lagrangian models. And between these models, one of the most important is Chimer, that is the most used among Europe. And these are the tools that we use to understand how air quality is dispersed and how air quality will evolve in the future. And this is a little bibliography about air quality dispersion and some of these models. And if you have some questions, don't hesitate to ask me. Thanks very much.
Thank you, Eduardo. Sorry for interrupting you there at the end. I was so focused on your talk, I also lost track of time. I think we had already a question for Sergi. I'm not sure you want to ask it in person or if you're happy that Sergi just responds.
Yes. Let me check the question in the chat box.
No, sorry, it was a question for Sergi.
Ah,
Yes.
okay. Sorry.
Oh, no problem. Can you hear me?
We have a raised hand. Okay, we will go to you,
Yeah.
Nicole, in a moment. Go on, Sergi, please respond.
Yes. Can you hear me?
Yes.
Okay. Let me check the chat. So there is one question that it's for me, and Nuria's question, maybe it's for me, but I'm not sure. I think it's for me, isn't it? Nuria's question too or not? Two questions.
Depends on what sensors Isabel is talking about, but maybe we go to the first question and then we can go to, we have only 5 minutes now.
Yes, so it's not an easy to answer question. The accuracy of the compact sensors compared to the reference sensors, and especially you are asking, Cyril, you are asking about the PMs, VOC, PMs, and CO2. CO2 is particularly difficult to measure with compact sensors without recalibration. If you are not recalibration a CO2 sensor, very easily or it doesn't have an automatic calibration, very easily you will go to errors of 300 ppm. If you are recalibrating the CO2 sensor, you will be around errors of 50 or less. You can get to less than 100 ppm error, okay, for a CO2 sensor. That's the state of the art for compact sensors. Regarding the particulate matter sensors, for PM10, they are not really very effective, the compact ones, not a lot. And PM1 and PM2.5, the compact sensors do correlate pretty well with references. So they can be mostly. Of course, there's a lot of manufacturers. There are some that are not so reliable, but in general, the ones that are in the range of 30 euro or more will provide a good PM1, PM2.5 normally. If you go down to something like less price, then it's not so sure that you will get good correlations. But in general, they work well. VOC is for VOCs, it's a complete mess because VOC, they respond to many different sensors, and you can only get qualitative measurements. They will never be anywhere near comparison to a GCNS. No way. So a general VOC, a sensor that is labeled as VOC sensor you can only get qualitative measurements, never quantitative. And I don't know if the second question is for me.
No, I think it's for Nuria.
Okay.
Thank you so much, Sergi. Nuria.
Yeah, I think probably we can answer it a little bit between Sergi and I. Isabel is asking if it's possible to get a list of sensors. I will say like not a full list of sensors, because the market of the sensor systems is changing so rapidly, and there are like so many companies nowadays that are integrating sensors, right? Like so. I'm not sure, like if you were meaning like what you can get is a list of what is possible to measure nowadays with sensors and what is the accuracy. And if you're interested, I can post it after some list. There's like some American website where they are testing sensors, and then you can get a list of some of the sensors they have tested and the results they obtained in the tests. And the data collected from the sensors, if it's publicly available, also a little bit like the same answer as before. I think nowadays there are many initiatives monitoring air quality, and there is no standardization in the way of that the data is shared. So sometimes it's in different silos, no? So you have, for example, like some big data gathers with sensors. Can be Purple Air, is very common very popular in the United States, and they have their website. In Europe, you have a sensor.community, also a citizen science or community-based monitoring. They also have their website. You can have also companies like Better or Hopu, and that they also have their systems, and or Early in Poland, where they also have their website, and so on and so forth. So there are many places, but I'm not aware of any place where one can go and see have a full overview.
Thank you so much, Nuria. I guess we will do one more question. Nicole, if you want to go ahead and unmute yourself.
Yes, thank you. I have just one question for Eduardo and another one for Sergi, if we have time. So the first one for Eduardo is in a context of a city, for example, like Ancona, how much should be dense the air quality network sensors in the city? I mean, what's the expected coverage that we should have, like in terms of kilometers, to have an overall idea of the air pollution of the city?
Yes, that's an interesting question, and more than the perimeter of the city or the area of the whole city, the most important to have a good idea of how air pollution is distributed is to define the resolution of the model and the resolution of the data. As Nuria has explained before, more cities have only 2 or 3 air quality stations with some gaps. The best way to address this is to have a good modeling is to have that is called hyperlocal data. Is to have data that comes from a lot of sensors. Now have a inventory of emission with good resolutions. I mean, to know the emissions, for example, with a resolution of squares of 1 kilometer per 1 kilometer. Let's say an example. And in this sense, we can compute the air quality and the concentrations with high spatial resolutions. That means that we can know the concentrations in high liter space, for example, squares, as I said before, of 1 kilometer per 1 kilometer. But so the most important is not to define an area to cover all the city, but the most important is to have high resolution data to do this.
Okay, thank you.
Nicole, do you think we could save your question for the end, or is it very related to what you just asked?
No, we can save it for the end.
Okay,
Yeah.
we will start with your question.
Sure.
Thank you.
Thank
So
you.
now we pass it on then to Francisco, who will talk a little bit about greenhouse gases.
Good morning, everybody.
I will let you know once you have 2 minutes also.
So in 6 minutes. So I have to talk about a very an overly complex topic, and I have only 8 minutes to talk about it. So sorry if I miss a lot to talk about a lot of topics. The first thing I would like to do is to to clarify 3 questions. What's global warming and what's climate change? Basically, climate change is it's a long-term change of the weather patterns everywhere around the globe, around the Earth, and they are not caused mainly by humans. They have been happening through all the ages, through all the eons. We didn't cause the glacial periods that happened 1 million years ago. They happen. They are climate. It's something that happens. What's the important thing to know is what the global warming is. This is what we are really doing. We are changing the way these climate patterns change, would change on their own. And this is happening and accelerating since we started, we in the different places of locations of the Earth entered into the industrial era. Okay, we are generating some greenhouse gases, and we are basically altering the atmosphere composition. And this is causing basically more extreme weather events. And here in the European Union, basically, we are heading to a reduction of the food production and, well, an impact in all the economical sectors. Well, I'm going to talk about what our greenhouse gases are. Okay, in the Kyoto Protocol, like 25 years ago, there was the United Nations. There was a United Nations meeting where they agree with definitions. Okay, mainly there are 2 kinds of greenhouse gases. The first ones, the non-fluoride gases, can be created naturally by the human beings, and the fluoride gases are only created by the human beings in industrial processes. Basically, the non-fluorinated gases are the CO2, the methane, and the nitrous oxide. And well, the fluorinated gases, there are many, and these are the 4 main families of fluorinated gases. Well, the important thing is, okay, there are a lot of gases, a lot of things that must be taken into account. When we start to analyze and compare what are the main factors driving the global warming created by the human beings. Okay, so basically the scientists came along with a solution. They basically each gas has a global warming impact. They have every gas has a lifetime, a lifespan till they decompose. So basically the scientists said, okay, we make a list with all the effects, the expected global warming impact in 100 years, and we normalize it to the CO2. So we get then they came with a unit, the equivalent CO2 global warming power, and all other gases are evaluated according to these levels. Okay, and this basically is useful, just as I said before, just to quantize what's the real impact of each gas, each industry, everything into the global warming. Okay, and well, that's it. Here I give some graphics, basically just to illustrate in the European Union which are the main industries producing that have a global warming impact. Okay, mainly in the European Union is the energy, then the industry and the agriculture, more or less the same, and then the cleaning, the waste management industries, yes, cleaning whatever we produce and what we leftovers. On the right, we have in exchange the gas emissions produced by the European Union. Just keep in mind, okay, that although that the 80% we produce the 80% of the global warming is produced by CO2. Okay, and then the others also have well, are produced less. But we should keep in mind that each gas has a different global warming power. So the methane, it's 25 times this contribution when they are compared. So basically, other gases has also a great impact to the global warming in terms of global warming power. Here, basically, I would like to compare to give a glance to the impact of each state into the production of global warming gases by each state. Okay, China is the largest, okay, and the most industrialized one, so it's leading the list. Okay, then afterwards the states. But if we check it, we compare it according to the per capita emissions, China becomes, it's more or less like the European Union, and well, there is a real range. Yes, I wanted to focus on this. And now I will talk about budgets, global greenhouse gases budgets. Okay, basically how the emissions, the net emissions of gases are quantized. So there are these things, these budgets. Okay, in this case I have the CO2 budget that, okay, through this span of time there was this net contribution to the atmosphere of CO2. Basically we can see here that there are enclosed the anthropogenic sources of gases are here taken into account. Also the sinks that basically the ecosystem can absorb greenhouse gases. So it's a source, a sink of the gases. And there are other, the ecosystems itself also have some cycles. Okay, they produce global CO2 in this case, but they also absorb CO2. I mean, when spontaneously a tree burns, okay, it's producing CO2, but also when trees grow, they absorb CO2. It also happens with the seas. Okay, they absorb the CO2. Okay, basically, and it's deposited at the ground, at the seabed. Basically, by chemical reactions, they become like something that has mass as is deposited.
2 minutes, Paco.
Okay, basically there is a nice important thing here. Okay, the global warming is accelerating, also it's altering the ecosystem. So the capacity of absorption of the ecosystems is decreasing. Okay, basically the seas can absorb less greenhouse gases as the temperature increases. Okay, and also the vegetation is less effective. So it's a fish that beats its tail. Basically, it's a problem that it realiments itself. For NO2, we have also the CO2, sorry, the methane emissions. Well, the methane emissions basically are produced by the fuel industry and the agriculture. They are also created by the nature themselves, and also well, there are the sinks of the different sinks, the natural sinks. I would like to say that greenhouse gases are also toxic in some cases. They can kill people by suffocation, by substituting oxygen. But, okay, all gases can kill us if there is a large enough concentration and they deprive us of oxygen. But some gases can also hurt us. In this case, CO2 and methane basically can kill us by suffocation. There is another gas quite important. It's the nitrous oxide. This is used, is produced intensively by the industry and in the agricultural uses by the inefficient use of nitrates to help grow the crops. Okay. And this one is also created by different, well, in the wastewater industry and, well, and other places. This gas in special is also neurotoxic. Okay, this is the typical the love gas. Okay, it was used as for the surgeons just as an anesthesia, but it also is dangerous for the people. It creates the neurological damage and alters the DNA. Furthermore, there are other gases nowadays that can also, they seem they have some impact, global warming impact, like the tropospheric ozone. Okay, it's not clear, but studies indicate that it also impacts, it facilitates has a global warming power. And basically, I will leave it here. Thank you for your attention.
Thank you so much, Francisco. We have now again a few minutes for questions. As promised, Nicole, if you want to start with your question, and anyone else who has a question, you can put it either in the chat or raise your hand. You may ask your question, Nicole. You're muted.
Oh, sorry. Yeah. So the other question was for Sergi, but basically was regarding the particular matter centers, because I was curious about the reference method, so the TOM and the other part, the other methodology for measuring PM. I don't understand. Are they real time, or you have to take the sample of air, for example, and then you have to take back to some lab that has the reference methodology?
You have both normally. Reference stations have one real-time determination and then another more accurate, slightly more accurate sequential. Sequential means that there is first sampling and then analyzing.
Okay.
So there is an absorption period and then analysis. Simply, well, the analysis is only weighing with the balance, the scale, measuring the weight, the mass of the absorbed in a filter.
The only drawback is that they are very, very expensive, I guess, if compared with, for example, light scattering methods for measuring PM.
Yeah, completely. 1,000 times, well, maybe 500 times, or
500 times.
100 to 500 times more expensive a reference PM method compared to a compact.
Okay. Yeah. Thank you.
Thank you. Do we have any more questions? Maybe some questions for Francisco, who just presented.
Maybe I can ask something. Francisco, you said the ocean now cannot absorb more, or due to the temperature increase, cannot absorb more CO2. Is this only because of that, or are we also reaching a concentration problem?
Basically, the temperature of the oceans is also increasing, okay, and as usually the gases are transformed in something different. I don't remember the methane and the CO2 by chemical reactions. It deposits. It becomes something like it has some names. It has mass and it deposits at the bottom, but this composition is kept under certain temperature and pressure conditions. As we alter the temperature of the oceans, these conditions, the amount of places where these sediments are deposited and stably, change. So basically, in some places they become again gas and they go to the surface. They go to the surface and enter the atmosphere, and that's what's happening with the oceans, and also with the ground, okay, with the permafrost and these things, it absorbs, but to the change in the climate change, basically the temperature changes and the gases are coming back to the atmosphere.
Thank you.
Thank you, Francisco. Vangelis, I guess you will have the last question before we close.
Yes, my question is not on the scientific content of this great course. Just organizational. Shall we have a second part of this webinar?
This is under development. There will be more information on this soon.
Okay, great. No, I don't have questions on the details. Just to say congratulations to all presenters. And as you can see, I have managed to open my camera. If you want to give you a tip.
Thank you, Vangelis, for doing this at the very end.
I can say how I did it, actually.
Perfect.
Okay.
Okay. Well, before we say goodbye, I just wanted to say one more thing: is that both EXA and SOCIO-BEE are very committed to creating inclusive and equal spaces. Unfortunately, we were not able to secure a better gender representation for this webinar, and we wanted to apologize for that and say we will definitely do better next time. And with that, I guess I will stop recording.